Hello and welcome back to Calculus 3. Section 11.8, Curves in Space. We are late today with the stream because of the SpaceX launch, so we watched the videos, discussed a lot of topics regarding that and the implications of it. And now we are going to talk about length of curves and tie it into the whole launch, hopefully, by the end. So, brief discussion on the past. You have the XY coordinate system, and you have straight line from point A to point B. And if you want to know the length of that line, you will take the tape measure and stretch it between 2 points and give the answer in meters or feet and call it a day. If you have the curved line between points A and B, and you clearly can't straighten this out to measure, we learned in Calculus 2 formula, which states that the length of the curve is equal to the integral A to B square root of 1 plus the derivative squared, derivative of x squared, dx. Now, we are also used from Calculus 1 to think that integral is supposed to give the area. But then you can quickly see that this is actually one-dimensional equation because, roughly speaking, the square and the square root cancel. They don't cancel because 1 plus. But let's ignore 1 plus. So square and square root would cancel, and then you have the integral of the derivative. Well, they cancel, just leaving f of x behind. So this is a one-dimensional equation. Now when you put all other bells and whistles, 1 plus and so on, it gives the length. Now the proof of that is in, oh come on. The proof of that is in your Calculus 2 class. Today we are going to change this a little bit. We are going to bring it into, we're going to give it a new light. So instead of me working in the Cartesian space like this, I can work in polar, and I can also work in parametric, right? So what do I have? Oh, software is being annoying now. Keep erasing stuff I write. So where do we begin? First off, those of you who are in honors, please go and review the derivation for this formula. And if you have any issues, see me. Derivation is through Pythagorean theorem. Right, and you can write the Pythagorean theorem, and you will get this quickly. Now I want to move from here into a parametric case. Come on, stop it. It keeps erasing stuff that I write. It's really annoying. So we can look at this formula A to B as square root of 1 plus dy over dx squared dx. And what I can do is I can multiply here, and this is the trick, again, honors option, pay attention, dt over dt. And what I'm going to do now is rewrite this. So this is a mathematical manipulation that we are doing here. I am going to rewrite as dx over dt times dt. And then I'm going to take this dx dt and stuff it inside the square root. Now when you do that, it picks up a square because it's going into the square root. So now the next step is to have 1 plus dy dx squared times dx dt squared, and you just have dt outside. And now when you distribute this dx dt squared, what you get is 1 times dx dt squared is dx dt squared. And now can I have one of the iPhones? I really need to break something. It destroyed everything. Everything. The square roots are in the right spot and the rest is just gone. I have to move back to my Surface 3 because Surface 4 is not working. Look. Like the whole lecture is gone. And no one knows what's the issue. No one knows what's the issue with this. It just does this. I updated, I reinstalled, did this 5,000 times, and it keeps doing this. It's syncing over here in the corner. The little green icon shows up in the corner when it's trying to sync with the cloud to save all the lectures. And it just kills it all the time. So, again, 1 plus dy dx everything squared, dx over dt, dt. Then this goes under the square root. So this is the old, keep it in parentheses, times dx dt coming in, has to be squared now. And then dt stays. And then when you multiply, there we go, again. At least it didn't move stuff, so I can quickly write these things, but maybe if I restart, I don't know. Now when you multiply, you get dx dt squared, which is the when you multiply by 1. And then when you multiply these two, dx squared and dx squared cancel, and you have just dy dt squared stay, and you have dt. And now in terms of parametric equations, clearly this is your dx dt, that's f of t prime. So you have a b, this is f of t prime squared plus g of t prime squared dt. And this is the parametric form for length of the curve from 2D. So 2D parametric form, 2D parametric form for the length of the curve. And something disappeared again. I just moved everything again. This is so annoying. So now, maybe if I save them locally instead of the cloud, and just keep hitting save, save, save every time I write something, just on a quick draw, save, 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 save. So it can't move things. Once I have the parametric form in 2D, I can quickly upgrade that to 3D form, where the length in 3D is going to be f prime squared plus g prime squared plus h prime squared. They're all of t. And I'm going to put that in this thick box because that's the 3D one. We want the Calc 3, right? Everything is gone again. So 2D, 3D. What was the sneeze? Good. Nice. 3D parametric form for length of the curve. Now this is in terms of parameter t. Parameter t is going to go from 0 to 1, 0 to 5, whatever, right, to give you the endpoints of the curve that you're looking for. Now to connect this to what we learned before, we know that vector r, our vector valued function of t, was f of t, g of t, and h of t. We know that one. And we know that r prime, which was also called velocity, was f prime of t, g prime of t, h prime of t. Now we also know that magnitude of the velocity, which is called speed, thank you, is going to be f prime squared plus g prime squared plus h prime squared, right? Isn't that what we have in the formula? Look quickly before it disappears. So that's exactly what we have. So I can now recast this formula here, and now the whole software crashes. Yes! We cannot win. The AI is too strong. Oh, come on! Restart the program. All right, let's see. All right. Apparently stuff is still there. Rewrite the formula as length of the curve is integral a to b square root of vector v dt. This is just the other form of the same formula. Now I'm going to argue that this formula needs to make more sense to you than the one up there, because the integral of velocity is distance. Shall we repeat together? The integral of velocity is, yes, good. Right? So, there you go. So the speed and, oh wait, why put the square root? Woohoo. Sorry. No square root. No square root. Square root is the part of the formula. I just noticed that. Sorry, no square root. You can also, if you want to, look at the formula as integral of r prime dt, but you better know that r prime is the velocity, otherwise doom in this class.
So that's velocity or speed?
Well, velocity, and then when you take the absolute value of velocity, you get the speed, which is what introduces the square root and squares and everything else. So integral of speed, this is integral of speed. Yeah, the length, the path, of how far you went. Great. Now, when you know the path that your, let's say, rocket is going to take, you are going to have that path expressed as parametric equations, and your parameter t is time, because once you go 10, 9, 8, 7, right, go all the way down to 1, the clock starts ticking as the rocket goes up, and it's going to cover that parametric path where parameter t is evolution on that path in time. And you can go and build up your velocity equation, you can go build up the distance and length and everything else, and then you have those little apps in a corner that measure everything. And, you know, it's, I don't know, these things are fascinating to me. If you don't like them, then just change your major. I'm serious, you're sitting in Calc 3. If you don't find that stuff interesting, just don't be here. I'm sorry. That's life, okay? So now we can quickly compute the path, let's say along the helix. If I have a helix, which is just that spring, and let's say it's a linear helix, we can describe this helix as soon as I restart the software. Yeah, I should definitely restart, but then I have to restart the stream and everything else. So let's say this might... Really? You killed my helix. It was perfect. By the way, nothing can tilt me now because of the successful launch yesterday. Well, actually, that's not true. Like, if Steve Jobs is to come back from the dead, that will upset me a lot. But other than that, nothing can tilt me. I hate him with every core of my being. Like every inch of my... And everything he represents. Which is everything that's wrong with this world. Like him and Hitler. Like, that's like the two. Like the alpha and omega of everything that is bad with society ever. Anyway, so helix. We have our R, which is going to be, say, 3 cosine t, 3 sine t, and t, which will make these guys to be 3 and 3 on x and the y-axis, right? And at this point, I can just ask you what is the length of the curve if I'm going to let the, I don't know, ant climb up this spiral, the spring, for, let's say, 10 seconds. So what is the length of the curve? How far would the ant go if I let ant travel 0 to 10 seconds up the curve? So at this point, you have your limits of integration, 0 to 10. You have your functions f, g, h to stuff into the integral, and the rest is algebra. Go on, have fun. And I will solve the problem once you attempt. All right, so let's try, see if this is going to hold up. So L equals integral from A to B, so now that's 0 to 10, right, 10 seconds. Square root of the derivative of 3 cosine theta is negative 3 sine, well, sine t I mean, not theta, plus 3 cosine t squared, and then plus the derivative of t is 1, so it's just 1 squared, which is 1 dt. This is integral 0 to 1. You have square root of 9 sine squared t plus 9 cosine squared t plus 1. And all together is 10, right? Because you factor out 9 from the first two, and you have sine squared plus cosine squared, which is 1. So what you get is that this is equal to integral 0 to 10, the square root of 10 dt. And that is going to be 10t, root 10 t from 0 to 10. And the answer for this length, L, equals 10 root 10. 10 root 10. And let's say this is in feet, so it went, climbed about 30 feet. No plus is a definite integral. Right? Definite integral gives us a number. And that's it. So that's the length of the curve using parametric form. You can use length of the curve, parametric form, 2D in the book it's done, to prove the circumference of the circle. I also do that in Calc 2. So now, they have more examples, so obviously we'll do a whole bunch of homework questions to practice. We have one more form, and that's the polar form. And in the polar form, again, for derivation, for honors. So for the polar form, you will start with parametric length of the curve, which is dx dt squared plus dy dt squared dt. And you are just going to take the parameter, instead of to be time, you are going to change the parameter into angle. So now you have alpha beta, and you have dx d theta squared plus dy d theta squared d theta, where theta is angle. So we are using the same formula. And instead of the t, we are using d theta. And now we use the conversion from, again, Calc 2. In chapter 10, we learn that dx d theta, well, actually, I can show this step. I don't think the book doesn't show. If you remember that x is equal to r cosine theta, and r is f of theta. So technically, x is f of theta cosine theta. So what's dx d theta? Dx d theta is the product rule of these. Copy the first times the derivative of the second plus copy the second, cosine theta, times the derivative of the first, which is f prime of theta. So we have that the dx d theta is equal to f prime of theta cosine theta minus f of theta sine theta. This derivation was done in your chapter 10 in Calc 2. Now, you have another one for dy d theta, which was f prime theta sine theta plus f of theta cosine theta. These two plug in and clear the algebra. That's all you need to do. These are very messy, very long expressions, because you see that dx d theta is squared. So you have to square this thing, and you get very long expression. Then you have to square the one on the bottom. You get a very long expression. When you clear the algebra and they cancel beautifully, it all gets compacted. So plug in and clear the algebra, or use the algebra to clean up expression, whatever. It simplifies to L equals alpha to beta square root of f of theta squared plus f prime of theta squared d theta. So it cleans up very nicely. So it's going to take you, 10 minutes or so to go to this. Again, honors. And that could be one of the questions for the test, but probably not, I don't know. And this is your polar form. Now, this is a 2D polar form, and you are not going to have a 3D polar form, because polar coordinates are exclusively 2D. In chapter 13, we are going to build polar coordinates into cylindrical and spherical, but not here. So the arc length and the polar curve is going to be just this equation, 2D equation, and that's it. And yeah, I hope you're not disappointed. That's it. Now what you do is you just take... Let's prove the circumference of the circle with this. It's a problem, right? So prove that C is equal to 2 pi r. That's what we have, all right? So what do I have? Function, which is going to be circle. Now observe that I say function. Isn't that contradiction in terms? Circle, wait, fails vertical line test. Yeah, it does, but it doesn't fail vertical line test in polar coordinates, right? In polar coordinates, r equals f of theta equals 2 is a circle radius 2, right? So yeah, our function is just r equals capital R. So we are actually looking to get 2 pi capital R as the answer. So that r, if you don't want to do it in general terms, the honor is better, you can just replace capital R with 5 and come up with 10 pi at the end. So that's what we're doing. So what am I going to do? Well, I have that the function is r equals capital R, and then clearly the, oh sorry, function I wanted to say, so f of theta is r, and f prime of theta is 0, because the derivative of capital R in terms of theta, well, r is a constant, which is the radius of your circle, so r is 2 or r is 5, whatever it is, derivative of that is 0. So now I set up my length of the curve integral. The angle is from 0 to 2 pi because I want the circumference of the entire circle, right? And I have a square root of r squared plus 0 squared, the theta. And you can quickly see that you're getting 2 pi because you are integrating r squared. So, I mean, square root will cancel that square. So what do I get? What do I get? Zero, 2 pi of r d theta. When I integrate r d theta, I get r theta, computed from 0 to 2 pi, 2 pi r, minus 0 is 2 pi r. And there's the proof for the circle. So next time you're tutoring someone in 7th grade and they ask you what is the formula for circumference, you tell them it's 2 pi r because you're paid to do that. Then they ask why. Pull up a chair. Pull the sleeves up. And if you have sleeves. You don't have that step. You skip the step of doing this. Yeah, I don't have microphone to drop it or anything. Just we're done. Done. Bye.